So let's begin. Hi, everyone. So this is lecture 5. And, I feel like I'm saying this all the time, but this is, I think, the last like build-up lecture, the last lecture in which we build stuff, and I kept saying that. And from next time, you'll see like more interesting stuff happening, but today we'll still have to go through these parts of the theory. Some would say this is the art, like setting up the right definitions, but that's true also. So as a recap, like a very quick recap, last time we defined this notion of a function field. We actually had a more general definition, but then we restricted to the case of one-dimensional, like one variable function field, and we had an alternative characterization of that, and I'm going to use that as the definition. And so, a field extension f over k is a function field if three things happen. First is that there exists some x in f for which this degree extension is finite. In the original definition, there was something about finitely generated stuff, but this is the alternative definition. Secondly, the field of constants is k, namely everything in f which is not in k is transcendental over k. And third, just as a minor technicality, f is not k. Okay. And but by the way, the name is a bit funny because it's called a function field, and it's not a field, it's a field extension. And the reason is historical. Initially, people studied this when k was like fixed to be complex, the complex field, like in the geometric, from the geometric point of view, rather than the algebraic number theoretic point of view. And so they consider the field f only, but we are going to be interested in the field extension. We are going to give some emphasis to k. This is the symbols in our code are going to come from k. So we care about that. And it's called a function field, but it's actually a field extension, not a field. And we said all that, but these are really functions in our mind. These are functions that we are going to evaluate. These are the constant functions. If the definitions are going to do what they should do, but these are going to be the constant functions. And the points at which we are going to evaluate are the places. Okay? We're going to connect all of these, but that's what you should have in mind. And now moving forward, I'm still in the previous unit, by the way, just we didn't finish it. It will take like half an hour more. So I want to define the notion of a place of a function field rather than a place of a field, which we defined. So let f over k be a function field. So ff from here on. A place of the function field. So we define the notion of a place of a field without any context of some underlying field. And kind of want to, I don't know, generalize that or something, is a non-trivial, actually it's a restriction, non-trivial place of f. So just as a reminder, a place of f looks like this with the usual things that we want from a place to have. But we want it to be non-trivial, so at least one element goes to infinity. That is trivial on k. Right, so places should be points, and a place of f over k is a place of f, but I want it to be non-trivial. So in my mind, I'm thinking of saying that there is at least one function that has a pole on that point in f. But it should be trivial on k, which kind of starts to encode the fact that we care about, that we think of k as constants, because saying that a place is trivial on k means that, well, no element here have a pole. And constant functions are like those functions that don't have a pole. polynomials do have a pole at infinity. So only constant functions essentially don't have a pole, and that's kind of what's been tried to be abstract in this definition. I think you saw some of this in the recitation, but let me prove a little claim, and not little at all, actually, an important claim, and there is a nice kind of picture adjoined to it. So I want to understand these places of f over k. So let f over k be a function field. And p, like this one, place of f over k. Namely, it's a place of f, which is non-trivial, but it's trivial over k. And let's denote its residue field. So recall the residue field, denoting it like that, but what it is, you just look at the image of f, but just remove the infinity. You look at all the possible values from L that are attainable. Okay? Then the claim is that this field, which as you see in the picture has this as a subfield of it, is a finite extension of that one field. Okay, so let me draw a picture and then it'll be maybe clearer to see. So what do we have? We have f. This is f. All the functions in the world. And then you have this, well, k sits inside of it. And then phi maps f to L and infinity, which is a kind of a board symbol, or there is a pole or a singularity or what have you. All singularities here are poles. So what do we know? We know that P is non-trivial on F, so at least one element goes to infinity, but it is trivial on K, so that element is not here, it's somewhere here. At least like one function has a pole at that point. So that goes here. Now, L could be like an overkill. I mean, maybe, let me draw it a bit bigger. L is just, it's not really, you can always take the real L and just extend it, and that's also a place. So what you really care about is like within L, you care about the image of phi. That's exactly f bar when you ignore infinities. So in the picture, it's like looks like something like this. I don't know what it means that it's larger than half or something. This is f bar. And everything in K doesn't go to infinity. So the image of phi, I mean, nothing here goes here, so phi maps K to something here. So this is phi of K, the image of phi, the image of K under phi. And the point is, and I think you said that in the recitations, this is an isomorphic copy to K. Right, because we actually said that also here, we said that any field isomorphism, any field homomorphism is actually a one-to-one, because the kernel is, because one goes to one and the kernel must be an ideal, and there are only two ideals, one of them is zero and the other one contains everything, so it has to be the one, zero. So anyhow, so this is actually isomorphic to K, and you have some freedom, by the way, on how you embed K inside F bar. But that's essentially the only freedom. An exercise that you have in the problem set says that two places are equivalent exactly when this thing is, well, of f over k is isomorphic. But you'll see that. So there is some freedom. This is an embedding, and there is some freedom in the embedding, but it's not important for us. Okay, so that's the picture. And what I'm claiming here is that this over that is finite. Okay, so it can't be infinite. It's like not much larger than the constants. Questions about what we are going to prove? Okay. Well, that's actually not so trivial. I mean, it's going to be short, but it's based on several things we did and several things that you will do in the recitation. So first of all, as the picture suggests, because phi is non-trivial on F, there is some T, not in K, that goes to infinity. So I'm going to use this t in the proof. And since phi is trivial on k, we know that t is not in k, as you have in the picture. And so what can we say about t? Can it be algebraic over k? Right, it has to be transcendental, right? Because all the elements in this like ring, not ring, algebraic ring, this geometric, everything here is transcendental over k because all the algebraic elements within f over k are already in k. That's k prime. So we know that t is transcendental. T in the picture is I don't know how to write it, transcendental over k. Can copy a bit. So let me have a little diagram. We have f, we have k, we have k of t. Right? These are field extensions. I don't care about those. I really care about f hat over k or phi of k. But we have these field extensions, and you know that. So it's kind of going to be very similar to what we did. So let's consider this subfield of f. This is isomorphic because t is transcendental. This is essentially the rational function field. Right? T is a symbol. There is no polynomial equation in t which vanishes when you plug a t. And since this is a function field, f over k is a function field, the transcendence degree here is 1. And so T, like the set containing T, is a transcendental basis. Like this is a transcendental element, but what I want to say is that this is algebraic. Because you have only one transcendence degree, you can't have more. So this is algebraic. Right? Because the transcendence degree of f over k is 1, and T is transcendental. If this was transcendental, then transcendence degree would be 2 or more. So this is algebraic, and it's also finitely generated because f over k is finitely generated by the original definition, not the characterization, but they're equivalent. So we know that this is finitely generated, therefore easily this is finitely generated. We actually used that argument before. And so this is an algebraic extension, which is finitely generated. And so what is it? Right, it's finite. Right, a finite extension, algebraic extension, and finitely generated extension together implies finiteness. So let me cut it short and say that f over kt is finite, which is not what I wanted to prove. We actually did that in the proof of the characterization. We used exactly this argument in proving that the definition I gave here was actually equivalent to the original definition for the case of one variable. So I could have kind of maybe exported some of the proof outside and something, but so we know that this is a finite extension, but I don't care about that. I care about this thing. Right? It's not clear what's the relation between them. We actually kind of know that. In the proof, we know that there exists an x for which this is all, but now we just prove that for any x for which phi has a pole, it's true. It doesn't really matter. But I don't want to prove that. I want to prove something else. And the point is that in the recitation, the point is that we really understand this function field, like kt over k. This is the rational function field. You started to talk about it, and you actually almost finished talking about it. You have only one place, if I remember, place at infinity to talk about. So you saw all places of kt over k. This is a function field. So kt over k, it's called the rational function field. It's the base function field for everything that we're going to do. We understand all of its valuations. I mean, you understand all of them except one, and we're going to understand it today. And so you can trust me that what I'm saying here is true. In the recitation, you will see, so you'll prove that all places of the rational function field, namely places that are non-trivial here, that are trivial here, have, for that is true, they have a residue field which is a finite extension of k. I mean, that's what we want to prove for a general function. We want to prove that, generally speaking, regardless of what the function field is, the residue field as an extension of K, or this isomorphic copy of K, is finite. And what I'm saying is we just completely understand all the places of the rational function field. We look at them and we see what they are. They correspond to irreducible to polynomial, that's what you saw, and one place at infinity. And in all of these cases, these are finite field extensions. For example, they depend on the degree of the irreducible polynomial. For every irreducible polynomial, the degree of the extension is the degree of the irreducible polynomial. For infinity, just 1, so even better. So we understand this, and I'm claiming that from here we can understand, or we can bound f bar over phi of k, which is what we want to do. So, but at least we have that. And another thing that you'll see in the recitations today, I think, the index product of indices, good. So another thing that you will see is that kind of, I stated it last time. Another lemma you will prove, but let me remind you of it, is that forget about function fields. It's like for every E over L, just a field extension, not function fields. Any field extension that you would like. Okay. Well, yeah, well, and the place psi, let's call it, just to not attach to the field that we have of E. We have that E bar over L bar times V psi of E star, V psi of L star is bounded by U over L. Right, so if you have a big field and a smaller field, and there is some place of the big field, then well, we prove that the residue field. So you can take this place, you can restrict it to L, and you get another place. So yeah, it doesn't have a strict name here, but there is another place like psi restricted to L, and then we prove that the residue field of the smaller residue field is a subfield of the larger reducive field. Or more precisely, the residue field of psi contains as a subfield the residue field of the restricted psi to L. And that's the degree of the extension, which is not clear is finite, but that's what this theorem is going to tell you. And it's not only that, not only it's finite, I mean, assuming E over L is finite, not only it's finite, also the index of the groups, like of the images of the corresponding valuations, that times that is bounded by E over L. We are going to only use this one here, but we are going to use this one in a second anyhow for another proof. So we have this, and you're going to prove that. So that's just kind of a reminder of the future. And from this, you are done. Because this is what we want to bound. All right, look at the picture. This is exactly what we want to bound, f bar over phi of k, which is just k. I mean, up to an isomorphism. So let's break it down at kt. And let me just write k instead of phi of k. And by say breaking down, I mean you take your phi, you take your valuation f, and you restrict it to k of t. That's kind of the L, E, and that's L. So E and L in the notation. Yeah. So you look at the smaller field extension, like the smaller function field within the larger function field. And what we know, I mean, what we just proved here is that f over kt is, which is like E over L. This is E, this is L. So we have that E over L is finite. So that's finite in our notation, which means that this is finite. So this thing is finite. Right, because of that. Because of that, I don't know how to. Yeah. So this is finite, just plug in E equals F and L equals KT, which means this is finite, and that's exactly this thing when plugging E and L correctly. And this is finite because of the recitation. because we understand all the places. This is a place, and we understand it. So this is a finite extension also, and so the product is also finite. Okay, so the proof strategy here was to kind of look at a subfield, which is a rational function field within F, and look at and say, given the place that we got this phi, we're going to look at phi restricted to k of t. We understand it well. In this case, we know that this is finite. This is the residue field of phi when you restrict to kt. So you understand it well. You know that it's finite. You know all of them. So all of them are finite. And then you use some other kind of this machinery, which is non-trivial, to argue that this top floor is also not going to cause problems. So if f bar over kt bar is finite because it's bounded by f over kt, which is finite because it's algebraic and finitely generated, and so it's fine. A lot of things together, but the general idea is to use the fact that you can always take a transcendental element, argue about this, and argue about that. Questions? Yes. This is just breaking down this equality. No, that's just the general thing to. I mean, it's like you have like f bar, k bar, and kt bar. It's a subfield of that, and that's a subfield of that. This is k really, so I should say k or phi of k. Sometimes you write k bar like that, but k bar looks like an algebraic closure, so I don't. Well, no, that's a problem also here. Anyhow, so look at this, and I'm just saying that the degree extension of that is that times that, which is equality in fields. Right? If you have like two field extensions like that, then the degree of this times the degree of that is the degree of that. The inequalities are here. So this is finite, it's bounded by this. And this you don't really know or understand. It depends on the valuation and how it looks when you restrict it to k of t, but other than that, it's equality. Yes?
We proved in the station that k of t over k, we know all the places.
Yes.
K of t bar.
No. So I'm looking at k of t over k, and when I write bars, what I mean is that I'm taking, so you have this phi sitting here. Phi is a function from f to L or something, but you can think of it to phi of k, phi of f. Anyhow, it's a place here, and when you restrict it to here, you get another place, which in the notes is called phi restricted to this thing, and its residue field is denoted like that.
What do we know about the places of k of t bar over?
No, it's not bar. It's not the algebraic. This is the residue field. So you have this phi from f to L infinity. Sorry for the mess, but actually it's a good place to write it. And then you look at phi restricted to kt. That's what you do when you're here, right? And it goes to, it also goes to L. Maybe something smaller, but goes to L. And you know that both, so you know that the image of phi, this is what you call f bar. The image of phi of f when you remove infinity is that's the phi of f that you have. And same here, the image of this thing when you remove infinity, which is something smaller, it will sit somewhere here. It also contains k, but I just denote it as kt bar.
I understand. What do we know about kt bar over k bar? We only know about, we might be able to tell something about k bar t over k bar, because that's what we proved, but the bar is outside taking t.
So kt is the kt over k is a function field. We understand everything about it. And this is just, so this bar actually has a phi in it. It's like, depends on the phi. And what I'm saying is that in this rational function field, which we understand, this is one of the residue fields obtained by one of the valuations. And we know them. It's not another function field. It's the function field kt over k. And what you see here is a residue field corresponding to the valuation phi when you restrict it to the rational function field K2 over K. Okay. Maybe we can do it offline. Okay, so let me go on still. So good, so at least we know that this number is finite. Wow, the purple is hard to erase. And with this, so which one? This one? Yes. So that's because you understand all the places of KT over K. Right. So this is, yeah, because of the recitation. You'll see today. I mean, you actually know exactly what this number is. You look at phi, you restrict it. It's a place. So either it's the one you didn't see, infinity, or it corresponds to an irreducible polynomial. In the fourth case, this is 1. And in the second case, it's the degree of the polynomial. You can actually very explicitly understand it if you know how phi is restricted to K of T. So it could be any finite number, but it's a finite number. Because they are irreducible polynomial of every degree. But, so let me still move on, because otherwise we'll get stuck at some point. Won't construct the code. So given this, we can define the following. So let f over k be a function field. And let phi be a place. Of the function field, mainly trivial on k, non-trivial on f. Then this number that we just proved is finite is called the degree of phi, and is denoted deg phi. And then kind of identifying k with u of k all the time. Right, for example, it's a good name because in the rational function field, the degree is really the degree of the irreducible polynomial. It corresponds to the degree of the irreducible polynomial. So it's a good name. In general, these are not going to be in correspondence to irreducible polynomials, but that's a good name. And we proved it's finite, just giving it a name and a notation. And just observe that if you take two, what can you say? If you take two equivalent places, namely they send all the elements to infinity together. If one sends it to infinity, the other sends it to infinity. So if p and phi prime are equivalent under the usual equivalence relation of places, what can we say about the degree of phi and the degree of phi prime? Equal, exactly. I'll explain why, but then it's really the degree is actually a property of the classes, not of the individual places. And the reason is just because, what is f phi bar? Well, technically, it's kind of the image of, of phi inside L, removing infinity. But we had, when we constructed the places from the valuations and the valuation rings and the maximal ideals, we actually know exactly what it is. There is also always an isomorphism sitting here. But it's really this thing. Right, the way we constructed the place was to look at the projection map from O to O over M. And then we extended it by sending everything not in O to infinity, if you remember. So the image is just that. And for equivalent valuation, this is the same set. These are the same sets. So that's this is a real set theoretic equality. And that's isomorphic to f phi bar. Kind of by definition, by construction, by the way you constructed the residue field and the place from the valuation. So right, so the degree is a property of the classes, not of the individual places, and that's going to be good for us because it's not the right thing to work with places. It gives you too much freedom of how you embed K. You don't want that freedom. Questions? So couple more definitions, and then I don't know, maybe the concluding theorem of this unit. So say our function field. This is a function field. Valuation. I'm kind of importing everything, places, valuations, and etc. to function field and field extensions, whereas we define them for fields. So I just want to kind of put everything in the context of a function field. Okay, so for places, it's a place of f, which is non-trivial on f, and it's trivial on k. And I want to do the same here for valuations and so forth. So a valuation on f, a valuation of, well, a valuation on f that corresponds to a place phi of f over k is said to be a valuation of f over k. It's almost like playing with words, but not quite. So you have a function field, and you look at valuations of f. Now, a valuation of f doesn't know about k. Who knows? It defines on f. But some of the valuations of f happens to be, they correspond to a place of f, and some of them are going to correspond to places of f over k. Like they're places of f, but they happen to be non-trivial on f and trivial on k. Right? And a valuation that corresponds to a place of f over k that respects k and is non-trivial on f is said to be a valuation of f over k. I'm defining this, a valuation of f over k, using the definition of a place of f over k. Okay, but it's a definition. We are going to be only interested in those valuations. If valuations are point, then valuations that are not like that, they're weird. They don't respect the fact that k is constant, in a sense. But you don't like, you would like a characterization of when is a valuation of f over k without going to the places, like just looking at the valuation itself, without looking at the place, and see if it's trivial on k and not trivial on f, and so forth. And you can do that, right? So can you tell me when, in terms of valuation, when is a valuation of f happens to be a valuation of f over k? Namely, when it is, I wanted to, in terms of valuation, to express the fact that it's trivial on k and non-trivial on f. Exactly. So, except they're not zero, because it's infinity. Right. So, saying this is equivalent, right? So, a valuation of f is a valuation of f over k if it has no poles in k. You require poles, but if there is a pole, there is also a zero, and this is closed under product. So the valuation has to be equal to zero. Strictly speaking, I should say larger or equal to zero. But if there's some element here for which the valuation is larger than zero, there is another element here, 1 over it, which is strictly smaller than zero. So I summarize this by saying this, because I know that pole and zero come together in the field. If you have a function of a zero, there is another function of a pole. And you don't want it to be trivial. You don't want this to happen for f, right? Because you want to be trivial on k, and that's the way you can say trivial on k, and it's not trivial on f. And so you wanted there to exist x in f such that v of x is non-zero. Maybe I want non-zero, I don't know. Just, well, yeah, I don't care. So, right, because this will guarantee, I mean, to be non-trivial for the valuation to be non-trivial on F, it means that there is some element that goes to infinity. So the valuation is smaller than 0. But if there is someone like that, there is also someone that's strictly larger than 0, so you can just write it as inequality. Yes.
In definition, you're only speaking about a valuation that corresponds to a place.
Of F over K, not of F. Right?
So why don't you just the case that corresponds to a place of F over K?
Because I want it. I mean, yeah. So you can do both, and both of them are useful. It's like it's an equivalent. You can either talk in terms of valuations, or you can talk in terms of places. And if I would have written this, I probably would have needed to say that note it corresponds to places of F over K. So you can take this as the definition, and this is the characterization the other way around. But yeah, I don't know. You want to connect all the V's and P's, and so I think it's arbitrary. So we'll care about these valuations that are trivial on K and non-trivial on F. Okay. And no, maybe another definition, like in valuations, you have this notion of discreteness. Like a place doesn't really have a notion of discreteness. Well, you can look at the corresponding valuation. But discreteness means, in valuation is that the image is isomorphic to Z, right? So I'm going to import it to places. I could have not even defined it and say a place is discrete, and you would kind of understand that I mean a place whose corresponding valuation is discrete, but we are formal, so a place of F over K, of a function field, this is a function field. Every time you see like something like that, it's a function field, is discrete if its corresponding valuation is discrete. Right, and actually, if you remember, we didn't show how you get a valuation from a place. That was the hard part, if I remember correctly. And you can say maybe there are other valuations that you can get, and maybe some of them are discrete and some of them are not. But there are other valuations that you can get, but they are going to be isomorphic. So if one of them is discrete, all of them are discrete. So there is so it makes it's well defined to say it like that. Okay, so because I didn't show you how you get devaluation. When I say devaluation, it's actually when I say it's corresponding, I mean the way that we constructed it, and there are other ways of constructing it. And by its, I mean ours, our construction. It's not a unique thing, actually. Okay? By our construction, which I never told you, by the way, by our construction. Right, but good. So that's what I'm saying. I'm saying it's corresponding valuation, not corresponding congruence class. And I could either say that, and that's fine, or I could just write it like this, and then say, well, it's really a property of the congruence class and not the valuation. Just nitpicking here, but to myself really. But just to be clear, we are going to anyhow, in a short while, fix one valuation from this congruence class and work with it. But at this point, it's not fixed. Yes. Its image, like the V of V star is Z, isomorphic to Z. Oh. Yeah.
You have to say what is the component between
right, and I didn't. Actually, I didn't. Right. I mean, the reason I didn't is because of time, but the reason that was chosen to be off is because it's kind of more difficult to produce ordered group from the valuation. I was like greedily lazy. It was the right thing not to. But the theorem that we are going to prove is that all places of a function field, let me be celebrative, function field are what? Right. Thanks, Ita. And that's what I proved. I promised you a long time ago that at the end of the day, all the ordered groups machinery is going to, be forgotten because now we can prove, using this machinery, that really Z is the only ordered group that you will care about, or isomorphic copy of it. So let's prove that. Okay, so that's what we're trying to prove. You take any f over k, which is, a function field, and any valuation, any place that you'll take of f, which is non-trivial on f and trivial on k, somehow is going to have, the valuation is going to have, the ordered group is going to correspond to like one dimension, it's going to be Z. And the proof of that actually uses this little claim. So recall the claim that you actually strengthened, but recall that if you have two ordered groups, with a finite index, so I think what you told me last time just says that they are isomorphic. I think you're right, but I'm just going to use what I know is true because I didn't get the chance to think about it afterwards. And that's all I need. So if you have two ordered groups and they are one extends the other, then if the smaller one is isomorphic to Z, then also the larger one is isomorphic. I think we just showed that they're isomorphic, and that's it. And we had like two variants, either this, or if the smaller one is 0, then the larger one is 0. But these are two special cases of everything. Like if they're isomorphic, then for anything that you'll put, you'll get that they are isomorphic to that thing.
So let's say what is corresponding valuation? For f corresponding valuation,
Yes.
somehow you define it.
Right. Yeah, you are. Yeah. I thought it's just a small thing, but now it feels like bad here, right? Because you didn't even see the valuation. But yeah, I'm just going to use a theorem that is kind of to be valuation. Right.
Maybe like the all places of functions are the scale when you take this specific.
Right. That's true. But what the other thing we proved is that, well, yeah, we proved it. Well, no, it was part of the thing we didn't prove. That the bijection is between congruent classes of valuations and valuation rings, which corresponds to congruent places. And so because the theorem that we didn't prove actually tells you that you don't care who you took of these valuations because the bijection is between the congruent classes. It doesn't matter, but you need to prove that. So I need, right. Yeah, exactly. So with this, let's prove this thing. So so this is a recap, and now let phi be a place of f over k, and it's going to start as before. So then, take, it's not then, just kind of take some t in f, and which is not in k, like before. So you take an element which is in f, not in k, and then it's transcendental. And because of all of these finitely generated and algebraic implies finite, you know that as before, as in the previous claim, again, I could have probably took it out as a claim and not reproving it all the time, but you know that this is finite. Right? You know that this is algebraic and it's finitely generated, so it's finite. Now, by the other theorem that you'll see today, by the theorem from today, like days in the future of Tomer's, you know that the valuation, you know that the product of two indices is bounded by the degree extension of the fields, but I'm just going to use that part. Right, so this times the degree extension of the residue fields is bounded by this. I'm just going to use this one. This is finite. And so we know that this bigger group, like the image of phi over the entire F star, is a finite extension of the smaller group. So if I would know that this thing is isomorphic to Z, so if this is isomorphic to Z, then I'm done because of that. Because you have two ordered groups, one containing the other. Their index is finite, and the smaller one is isomorphic to Z. So the larger one will also be isomorphic to Z. So that's a theorem you didn't prove and you will prove today. And this is another thing you didn't prove and you'll prove today. Right? You're not only, when you study the rational function field, you understand all the places. So you know that, in the context of before, all the residue fields are finite extensions of K. But the second thing you know is that all the valuations are isomorphic to Z. Right there, yeah. So you'll see that. I mean, for irreducible polynomials, the ones you saw already, it's kind of the power of that irreducible polynomial that divides you. Really. So if V when you restricted to, if V or phi when you restricted to K of T happens to correspond to an irreducible polynomial, P of X, then V phi will tell you how many times P divides U, or well, minus if it divides the denominator. And anyhow, it's a number like a integer, so it is isomorphic to Z. And the infinity, I don't want to spoil it, but it also corresponds to a number. It corresponds to the degree of the polynomial that you're looking at, of the rational function and so forth. Anyhow, this if is actually is true. So, and because of that theorem, and that thing, we're done. Okay. Questions? Good. So the last thing I want to say before the break is a claim which I will leave to you. It says a result you will prove in the recitation. So the Tom will tell me if it's true or maybe it's an exercise. I think it's an exercise. I mean, in the sense that it's not so hard to solve. So you don't need Tomer. So, but it's kind of a deep thing. So following from what we did. So let F over K be a function field. Yes. Is bounded? Right, because we said that even this times it's something that we didn't prove and you'll prove today. Times the residue field extensions is bounded. Yeah. So there was something like yeah. Anyhow, so if you have a function field and you take X in F which is not in K, so I think of it a function which is not constant, then and I think you should be excited by what's going to happen now. There are valuations corresponding to this X, valuations V and V prime of F over K, so trivial on K, non-trivial on F, with, do you know what I want to write?
One of them is positive.
Very good. Right. So to every function which is non-constant has a 0 and a pole. Right? Because this is a function which is non-constant, valuations are points. And saying this is to say that X vanishes at the point V. So V is 0, like, in this sense, of X. But it really is the case, because if you look at phi that corresponds to V, that's the evaluation. So if you're going to evaluate X at V, what should you get? 0, exactly. Because that says that, same thing. That says X has a 0 at V, and this is the evaluation thing. And when you fix the point, it has a fixed point, but I mean, it has a point in mind, but given a function, it evaluates that function at that point. It looks different. This should be the point, and this should be the function. That's how it works. Phi of the point at the function is evaluating the function at the point. And if you think about it, this is equivalent, because this is saying, if you don't see, this is like saying that X is in MV, and MV is exactly the kernel of this map. Just make sure that you understand this. And this is saying that that X by the same reason X has a pole at V prime, because this says that Phi maps X to infinity. Phi of that V prime maps X to infinity, because it's not in O. Okay. Yeah, good. So that's a deep theorem, and it holds true in this general abstract framework. It's crazy. Okay, good. So after the break, we are going to move on, talk about divisors, the Riemann-Roch spaces.